In this video, we're going to look at how to read query plans that are more complex than what you've seen so far. Query plans are best thought of as being in a tree-like structure. The leaves of the tree we call nodes, and there are leaf nodes and parent nodes, and there's a hierarchical relationship between them. In this example, I've got a query that for each actor that has a first name of Mary, I return the number of films that they've appeared in. To do this, it uses a correlated subquery. I'll just run this query alone to show you what the output looks like. So this returns that there are two actors with a first name of Mary, and for each you get the first name, the last name, and the count of the films that they've appeared in. Let's now have a look at the query plan. It's quite a bit more complex than the plans that you've seen so far. As I mentioned, the best way to interpret this plan is to think of it in a tree-like structure. This bitmap index scan is a child of the bitmap heap scan, which is in turn a child of the aggregate. That all rolls up into something called a subplan, and in turn that finally rolls up into a sequential scan on the actor table. There's a hierarchical relationship. Notice as well that the cost tends to cascade up the tree. So this bitmap index scan, which you haven't encountered so far, but I'll explain coming up, ends with a cost of 4.48 to complete that execution. Notice then that that's the starting cost of the next node up the tree. The final cost of the bitmap heap scan is around 35, and notice again that that's the starting cost of the aggregate. So you tend to see this kind of cascading relationship with the costs in query plans. Not always, and there are some good reasons why that's not always the case, but most of the time. There are a lot of different kinds of nodes, and so far we've talked about sequential scans, index scans, and index-only scans. They're all different ways of getting data out of tables, and I'll introduce you to the final type that you'll encounter, which is called the bitmap scan. This entire structure, bitmap index scan and bitmap heap scan, whenever you see those two, they'll always go hand in hand together, and we just refer to them both together as a bitmap scan. A bitmap scan falls somewhere between sequential scans and index scans. They're typically used when you would end up reading too much data from an index scan, but too little to perform a sequential scan. A plain index scan fetches one record of data at a time. It goes to the index, finds the pointer to the actual table data, and then fetches the table data. That's totally fine if there's just a single match in the index, if you're just looking up one record, like maybe the primary key for a table. But it's quite slow if there are a lot of matches in your table, because it generates lots and lots of random disk access as you pull out different records from the table. What a bitmap scan does is it fetches all those different pointers from the index in one go, and it sorts them in the physical order that you would actually walk through if you were pulling these from disk. Accessing files from disk sequentially is a lot faster than just doing random access, and so the bitmap scan improves the locality of the references to the table, but it just adds a little bit more in terms of overhead with bookkeeping. A good rule of thumb is that a plain index scan wins for fetching a small number of rows, bitmap scan wins for somewhere in the middle, and a sequential scan wins if you're fetching a really large number of rows from the table. Let's now talk about the different kinds of nodes that you'll encounter when you're doing joins. Let's have a look at our relationship diagram. As a very simple example, what I'm going to do is join the customer table onto the rental table based on the customer ID. Let's write a simple query to do that. And for each rental, I'll return the rental ID, and I'll return the customer's first name from the customer table. Let's run this query. So pretty simple. And now let's look at the query plan. Some of the different nodes that are in play here are a sequential scan on the customer table, a hash, there's a sequential scan on the rental table, and then there's what's called a hash join. There's several different types of nodes that you'll see when you're doing joins, with three main ones, mostly depending on the size of the tables that you're working with. There's what's called a nested loop. There's what's called a merge join. And then there's what's called a hash join. A nested loop works by walking through one table, and for every row of that table, it goes to the other table and it looks up the matching row or rows. So it performs a join quite similar to how you might actually implement it if you were just writing code yourself. It's a fairly naive way to go about joining two tables together. However, it is very fast for small tables. So if you've got two very small tables and you join them together, look out for a nested loop. The next is called a merge join, and the way a merge join works is it first sorts each table, and then it walks through those sorted tables, joining them together in an in-order type of traversal manner. Sorting can be quite expensive, so there's a bit of work that needs to be done here, but this can end up being the faster approach for, kind of medium-sized tables. Finally, there's the hash join, which is what we saw used with the type of join that we did. The way a hash join works is it scans one table and builds a hash table, and then it steps through the other table, looking up entries in the hash table based on the keys. It can be quite memory intensive because it needs to build a hash table data structure in memory, and there's a bit of startup work that needs to be done as well, so it can have a slow startup time. But when you've got really large tables, it can be very quick. For the kind of queries where you might run into performance issues, you're typically working with pretty large data sets. So in most cases, what you really want to be looking for is a hash join. What's interesting about this though, is you may see instances where you don't get a hash join. The reason why is because Postgres has a parameter called workmem. Workmem specifies the amount of memory that Postgres is allowed to use. If building a hash would exceed that workmem value, Postgres won't even attempt it. And so this can be one instance where what you may actually want to do is temporarily increase the workmem, and you can even set that just for that individual connection in order to be able to get Postgres to say, okay, I've got enough memory to work with. I'm going to go with the hash join approach because this hash can now fit in memory. So as you're doing performance optimization work, look for a nested loop or merge join, and if you see either of those with really large tables, consider upping the workmem, even if it's just for that one single connection, just so you can get a hash join happening, and it will probably be much faster. So that's joins. There are a lot more nodes that you're going to encounter as you look at other query plans as well. You'll see a node specific to limit if you use the limit clause. If you do any sorting with order by, then you'll see a sort node. If you use grouping, you'll see a node that's called hash aggregate. And there's many more. I encourage you, whenever you see an unfamiliar node, to look up and do a bit more research about it. One final thing I wanted to show you was you can actually get different visualization tools for query plans. And pgadmin, which is a tool that is typically installed whenever you install Postgres, has a really nice one. I'll quickly launch it now and show you how to use the visual query planner. Okay, here I am in pgadmin. I'll expand servers, Postgres. I'll go into the VideoEasy database. I'll expand to the public schema, right-click on that and select Query Tool. With this interface, you can write queries just as if you were using dbeaver. Let's paste in that first query that has a correlated subquery. We can execute it by clicking this lightning symbol, and it runs just the same. But to actually make use of the visual query planner, I can get rid of Explain Analyze, and instead I can select this, the Explain Analyze icon. When I do that, I now actually get a visual representation of the query plan. You can see that it has the bitmap index scan, the bitmap heap scan, that rolls up into the aggregate, and then finally that rolls up into a sequential scan. You can toggle a few different options to be enabled with your query plan as well. So there's verbose, costs, buffers, and timing, which just give you some additional information when you hover over the different nodes. When you have really complex query plans with lots of children and leaf nodes and subtrees, using a visual query planner can enable you to read and interpret it much easier. Now that we know how to read query plans, let's next talk about some actual optimization techniques that we can use to improve our queries.